Okay, I've got a state of strain now, and I can do transformations with strain very similar to how I do them with stress. There's just a simple factor of 2 that shows up in the shear strain. Now, in this problem, we've got the state of strain, and we're trying to find the maximum, which again is what generally we're trying to find. Okay, now just because we set things up in our arbitrary XY axes doesn't mean that's where the maximum stresses and strains are occurring. So that's the point of these transformations: is find your state of strains on axes that make sense to us, in calculating, and then go ahead and do these transformations to figure out actually where the maximum is occurring. And that's what we're trying to find here. We're trying to find the maximum in plane shear strain. We're trying to find the maximum principal strains. That would be normal strain, like that. And again, these are just plug and chug equations, so they're not too difficult. But again, the whole point is we set them up based on our how it is easy to calculate it, then do these transformations to figure out, just because we said X and Y are horizontal and vertical doesn't mean that's where the maximum strains are occurring. So we've got to figure out where, in what orientation, and what those maximum strains are so that we can design accordingly. Now, again, equations aren't too tough. For our principal strains, 1 and 2, we just kind of plug in the equation. I'm going to drop the times 10 to the 6, add them later. All of these are 120 times 10 to the negative 6, negative 180 times 10 to the negative 6, and so on. I'm going to drop them just to make the equations a little bit easier to write down, but then I'll add them back in at the end there. Okay, and then plus or minus. The plus is epsilon 1, or the principal strain 1. Principal strain 2 would be the minus, and then it'll be the square root of 120. Minus a negative 180 over 2 squared plus 150 over 2 squared. And again, we can do this with stresses as well. Okay, just a little bit differently, finding stresses or strains. Okay, but the general equations look pretty similar. Calculating these, I can find that my maximum strain is 137.7 times 10 to the minus 6. And again, these are unitless numbers, okay, because they're strain. It's like, micrometers over micrometers kind of thing. And then minus 197.7. So you can see, okay, my maximum strain is not 120. It's actually 137. So just because I have an X and a Y axis doesn't mean that's where the maximums are occurring, okay? Similarly, my minimum is not negative 180, it's negative 197.7 times 10 to the minus 6. So again, just because I find what's going on in the X and Y axis does not mean that's where the actual maximum is occurring. I need to figure out kind of what orientation that occurs in. And to find that actual angle, I can do the tangent of 2 theta p for the principal angles equals 150 over, and again, these equations are in your book, okay, and they're very similar to the stress equations, okay. Strain is just using epsilons rather than sigmas, essentially. And again, it's at 13.3 degrees. So rotating this element 13.3 degrees in that orientation is where I actually have my maximum strains, and that's how the most strain is going to occur in that orientation. Now, I don't like drawing these because drawing a strained element makes it a little challenging, okay? But you rotate that 13.3 degrees, that gives you where your maximum strains are actually occurring, okay? I can do the same thing with the shear strain. Again, there's going to be a factor 2 that will not be there when doing it with stress. Okay, but again, the equations are very similar, and in the book you'll be able to find them. But we'll just write it down kind of quickly here. Again, there's a factor of 2 here. This would be 150. Okay. So from that, I can find that the maximum shear strain is actually, is actually 335. So again, just because I calculated in the orientation that I put it in a shear strain of 150 doesn't mean that's where the maximum, how the maximum actually is. And if I design only to withhold the 150, and I actually in another orientation have 335, well, I'm going to be in trouble. I'm going to overstrain the object based on my design. Okay, so we need to figure out what the maximums actually are. That's how we typically design, is so that they don't reach those maximums. Okay, and we can find the orientation, which is going to be 45 degrees off of the principal strain, just like it is for stress. Okay, but we can plug and chug into the equations that we have. That will be epsilon x, which is 120 minus negative 180 all over 150. And from that, I can find that the orientation is negative 31.7. So in that orientation, again, it's going to be a 45-degree difference from what I had with my principal strains. The maximum in-plane shear strain is actually rotating down 31.7 degrees. That's where that maximum shear strain is. So again, this is just to figure out what the maximums actually are, not just what they are in the x and y direction, and then what orientation those maximums actually occur. They're pretty easy to find just plugging and chugging, but then understanding what it is we're actually finding is kind of the trick here.